So the range of light that comes out of an incandescent bulb is not just visible. Can you guess what else comes out of an incandescent bulb?
Infrared.
Infrared, you got it. So there's a tremendous amount of infrared coming out of an incandescent bulb. And so what I do is simply hook two of them up and shine one at a bottle that just has air in it, and the other one with a bottle that has carbon dioxide in it. And wait about 30 or 40 or 50 minutes. And we look at the temperature change, and the one with the CO2 goes up about anywhere from 3 to 5 to 6 degrees higher, depending on how long, depending on how good the demo is working. So I'm sure you can figure out a way to put CO2 in a bottle. I just use vinegar, and I'll do it over here so I don't mess up the computers. All right. So I have baking soda. I didn't have time to make some 5% acetic acid. So this is my 33% acetic acid. So I'm just going to pour it in water and make some vinegar. So there it is. Exactly 5% acetic acid. Okay. And another thing, we even get into density, and this, this is way at the beginning of the year. We can already talk about density. Why is the CO2 going to stay in? Could you? Oh, or somebody?
I need you the PowerPoint.
I need you to hold this. So it doesn't.
I had to come all the way up here for this.
I'm PowerPoint person.
Oh, okay.
All right. So then the CO2 is more dense. It's going to stay in the bottle. It's going to push out the air. I think this would work much better if I had. I've been using this for a couple years without cleaning it out, so probably cleaning it out would be a good idea. And you just sort of gauge it, and when you think, gee, it looks like it's filled up with CO2, then you're done.
I'll test it.
Well, I asked the students how could we test that. I did this today actually, and one kid actually said, "Well, can't you pour it over a candle?" And it was amazing. I'm like, yeah, I can do it. But then we wouldn't have the CO2 anymore. All right. So you put the thermometers in. You take a reading before. You take a reading after, and they can see that the temperature goes up faster with the CO2 than with the air. Now, this did not work for me at all today.
Never mind. That's okay.
And if anybody, so I'm saying that because I now know I don't have any real faith. So I don't know. That's why I say I probably should clean the bottles. I really don't know why, what happened, what has gone wrong. And I just asked two students to simultaneously turn on the lights. And I do this right at the beginning of the period, and then at the end of the period, we look at the temperatures. All right, so that's my global warming extension of the interaction of light and matter. All right, so a lot of students have a hard time understanding the quantization of electrons. So Bohr's model, the one thing that we still have with Bohr's model of the atom is that electrons are quantized. And what does that mean? And so we talk about that. We talk about what a standing wave is. That an electron can only exist because it is a wave. This wave-particle duality, because it has the properties of wave. The electron can only exist at a standing wave. And this was a demo done by Paul Cash from Whitney Young at the North Central meeting a few years ago. I don't know if anybody's seen it, but I want to repeat it again because it goes along with what I subsequently want to show you. So I do need some help. You want help?
Oh, sure.
Okay, so you're going to stand over there. Oh, you made more copies?
Yeah, I did.
Oh, that's amazing. So, all right, so simply the idea being the different amounts of energies that are required in order to get more and more nodes in a standing wave. So
I'll let you go on hold.
So yeah, you're gonna hold. So here's one node. So how do you get more than one node? Well, you have to put a little bit more energy into it. Let's see if I can just.
You increase the frequency at which you move your hand up and down.
Ooh, you're very good. So here's two nodes.
She knowed that.
So the point being, in order to get more and more nodes, I'm not. Oh, there we go. So in order to get, thank you very much. In order to get more and more nodes, you have to put more and more frequency. I'm sorry, more and more energy into the wave. And so, if they can understand that and understand that an electron only exists at a standing wave, then they can understand why Bohr came up, what the science is, what the evidence is for Bohr's model. I can put this back in. For Bohr's model, where the electrons can only exist at very specific energies. Now, to drive that point home, I have one more demo. So this is the power. I have a PowerPoint.
Yep. That's me.
So standing waves.
Wrong PowerPoint.
Standing waves in musical instruments. A musical instrument can only produce a sound when it has a standing wave. So if it's a wind instrument, it will only produce a note if the sound wave in the tube, in this case a trombone, is at a standing wave. If you're bowing a violin, the string only produces a sound as a standing wave. So I have just fun with this. You know, I take this out and the kids are just staring at me like, what? What on earth is he doing? And do you really play that? Did you used to play it? I played it, so I played it in high school and college, but I remember enough to play a few notes. So the point of this is an analogy to the harmonics of the electron. So the electron, we can call them electron harmonics because the electron can only exist as a standing wave, just like the harmonics in a musical instrument. We call them harmonics, the notes that you can play, for example, in a trombone, when this slide is all the way closed. So the first one, I need a drink of water.
We all know. I guess
Is there anything?
There's a dance in it.
No, really, I can't get a note out of this. Okay, so that's the low B flat. And so what I've done here is relative energy emitted by the note. Okay, so next one. So I'm just gonna go up. Okay, so that's where I go. But the point is, number one, the relative energies can be equated with where the notes are. The energies in between the notes get closer and closer together, and in the next slide I'll show why that is. But in particular, I cannot play any notes in between these notes when I'm in first position because there is no standing wave allowed by the tube in between those two notes. So I can't get anything in between those two notes because the wave is disrupted, and that's the reason why we can't have electrons that exist between specific energies because the wave interferes with itself. And so the next,
Yep.
All right, so so here's a drawing of what the standing waves might look like. And as you can see, they're all standing waves, and they increase by one node as you go up each one, increasing by one node. But the energies, because here you're adding one node to one, that's twice the amount. Here it's only 1.5 times as much. What is this, 1.25 times more? So the amount of nodes by proportion gets smaller and smaller, and so the differences in energies get smaller and smaller. So I don't know if you think, well, any questions? All right, so so the last part of this is equating the standing waves with the allowed notes in the trombone, where the energies occur at standing waves, and then equating that with the allowed electron energies in hydrogen. And I spelled hydrogen wrong. And of course, just like I can play higher notes in the trombone, we can go to higher energies in hydrogen, and the energies as standing waves get closer and closer together. The electrons cannot exist in between because that would not be a standing wave for the electron. So that's, all right, so that's the end of that demo. And I'll do one more quickly. This is much more of a crowd pleaser. Well, they love this actually. Even if they get nothing out of it, they're very engaged. I think some of them get something. Anyway, all right. And I know probably most of you don't play the trombone. If you really want to do this, I'll be happy to send you the PowerPoint. And if you want to borrow somebody's trombone, it's probably one of the easiest instruments you could possibly play. All right, last thing is, so I like to show them what I like to show them that electrons, so this is actually before all of this. I like to show them that electrons have energy. Can we turn off?
I'm on it. Just front, back to.
This is fine.
Let's go big.
All right.
You can still see.
So I like to show them that electrons do have energy. So I just use a Tesla coil. Where's a plug? Yeah, I know what they're used for.
Straight.